So today in our course selected topics in decision modeling, we are going to discuss cutting plane method. That will be our 15th lecture, right. So as you can see that in the cutting plane method, in the last class we talked about solving a linear programming problem, integer linear programming problem, which is like this, that we have an objective function maximize z equal to 2x1 plus x2 subject to two constraints are given, both are less than equal to constraints, and x1 and x2 there are two variables, both of them are greater than equal to 0 and they are also integers. So how do we solve such a integer linear programming problems with the help of linear programming? So we shall discuss this problem at two levels. In the beginning we will try to find a graphical solution of the corresponding linear programming problem, and we see how we can modify this graph by making use of cutting plane method and successively reducing the solution space so as to have keep all the integer solutions intact and cutting down the current optimal solution. Is all right. So, from the linear programming we shall find the optimal solution, let us say initially by the graphical method, then we cut out the what you call your the optimal solution, but keeping all the integer solutions intact, right, and keep on doing this a number of times till we get an integer solution in the linear programming itself. Moment we have that, then our optimal solution, that is optimal integer solution, is found. But you can do it in a 2 by 2 variable problem very easily, but moment you have a bigger problem, this method will not be applicable because you cannot use graphical method to solve such problems. So, what should you do under that situation? We have to follow the simplex procedure. So, and next after this graphical method explanation, we shall then see how we can do this by making use of simplex, right. So, let us see how we do this through the graphical method. Now, you see this is the graphical solution for these linear programming problem. This one, the solution that you see here, this is not the integer programming solution, right. So, the what you see here, this is the solution for corresponding linear programming problem, right. So, this is the solution for corresponding linear programming problem. So, what we do? We take the x axis and the y axis, and then these 2x1 plus 5x2 equal to 17, we draw one line, 3x1 plus 2x2 we draw another line. So, as we draw these two lines and along with this x1 greater than equal to 0, and x1, this side is x1 greater than equal to 0 and this side is x2 greater than equal to 0, and then we find this solution space, right. So, that is our LP solution space. Now, in this LP solution space, we know that the basic feasible solutions are these corner points, this one, this one, this one and this one, and either we can evaluate, one of them will be optimal because optimal solution will lie at one of the corner points. So, either we evaluate the value at these 4 corner points, or a simpler method is also there in this case, that we find the profit line. So, this is our profit line, this is also the same profit line. So, move the profit line, right, parallel to itself. So, as you move the profit line parallel to itself, at some point the profit line will touch one of the corner points, and after that it will leave the solution space. So, obviously that is the point where we will get the maximum value of the function, that is the objective function. So, that will be our optimal solution. So, you know all these are very well known to all of you whoever has studied linear programming. So, our optimal solution will be then 10 by 3, that is x 1 value, and 0, that is x 2 value. So, what is the optimal solution? X 1 star equal to 10 by 3, x 2 star equal to 0, and what will be the value of z star? 20 by 3, because 10 by 3 into 2 and 0 into 1. So, that is our optimal solution. But we do not want this optimal solution, we want the integer optimal solution. Is it okay? So, obviously 10 by 3 is slightly bigger than 3, not an integer. So, this solution we shall not accept. So, what should we do? See, this is our LP solution space. We should see how many integer solutions are covered within this LP solution space. Alright, let us see what are they. So, cut it out and then go to next page, and here you see the same solution space is shown here, and all the integer solutions are indicated by a dot. So, these red dots, they are all our integer solutions within the solution space. So, you can see like this is 0 0. So, we have this is 0 0, then this is 1 0, 2 0, and then this point is 3 0, here 0 1, 0 2, 0 3, and etc., etc. For example, this is 1 1, this is 1 2, this is 2 2. So, sorry this is 2 2, this one is 1 2, this is this is 2 1. Alright. So, all these points you can identify. So, these are all the integer solutions which are within the LP solution space. So, you can see that your optimal solution will be in one of those integer solutions. It includes 0 0, but 0 0 cannot be optimal. So, this corner point cannot be optimal because this is not integer. This corner point cannot be optimal because that is also not integer, and this corner point which is the current optimal solution, this is also not integer. All right. So, we want to keep all the integer solutions intact, and we want to cut out solution space minimally that will cut this current optimal solution and will keep all the other integer solutions intact. So, how do we cut this solution space? Any guess how do we do that? Think over, this is the nearest integer solution which is available. So, how do we cut? Can we cut by taking a line, this one? Suppose I have this line and then I cut this portion of the solution space. Just look at this, this will cut the current optimal solution, and so this will be our new solution space. This portion will be cut off, this is the cut off portion. This is a minimal portion that we can cut off, but then it keeps all the integer solutions intact. Is all right? Now, interesting thing is that it can be done easily here because it is a 2-dimensional problem, and we can examine the graph very easily, but then if we have to solve it by simplex, there should be a simpler way of finding this particular line. Is it all right? So, you see what is this line? This line is x1 equal to 3, but we have to take this side. So, basically the constraint you are adding is x1 is less than equal to 3, right. So, that is the constraint that must be added in this, so as to accomplish what we are having here, right. So, let us see what it is. So, you can see here this is precisely done here, and after you do that, then what are your corner points now? Now, your corner points are 0 0, this one, the other corner point is your 0 0, this is one corner point, this is another corner point, this is another corner point, this is another corner point, and this is another corner point. So, we have 5 corner points. Now, the optimal solution at this point of time is your this point where the optimal solution is 3 x1 equal to 3 and x2 star equal to half, is all right. So, this is our new solution space. What will be the value of z star now? Because 2 x1 that is 6 and x2, so this is 6 and half. Look here, this point 3 0, here the z value is 6, right. So, this point is having higher optimal value, and as we have seen in our previous plot, the the profit line goes like this. Obviously, they are outside. So, this is the where so you see your earlier profit line, suppose I just draw those profit lines. So, you see roughly this is, that was our profit line. So, now the profit line has slightly gone inside, right. So, like earlier our optimal value was 20 by 3, I think, is it not. So, that was our optimal value. Let us see what was our optimal value in our previous slide. So, in our previous slide, our optimal solution was 10 by 3 and 0. So, 20 by 3 that was our optimal solution, and now our optimal solution is 3 and half. That means from this from 20 by 3 it has come down to 3 and half, that is 6 and half. So, 13 by 2, all right. So, 20 by 3 to 20 by 3 is 6.5 is 19.5. So, it is above. So, this value is exactly 6.5 and this value is more than 6.5, right. So, from a value which is above 6.5, our new objective function value has fallen to 6.5. So, what have we done? We have in a way reduced the the objective function value. That means, our LP solution was the best, but then in the search of an integer solution, we have come to a point where we definitely found a solution, but then again it is not integer, right. But then we should not lose heart, again we employ the similar procedure. So, what should we do? How do I find out another line that cuts off the current optimal solution and at the same time retain all the integer solutions? How do I draw the next line? So, again if you think, then the next line actually may join these two integer solutions and go further, is it not? So, is it a line like this? So, this line, if you really think of, this line joins the current integer solutions around this point, and the area which is here, probably if you cut off this portion, then you still retain all the integer solutions and you cut off the present optimal solution. So, that should be our next step. So, let us see how do we do that. So, again we do that. So, look here, then we have drawn this line which is your the next constraint line, and this constraint line can be measured as 2x1 plus x2 less than equal to 6. You know, this line that joins this point, the current the optimal solution, this will be cut off. This was the earlier optimal solution, old one, and this portion of the area which is cut out, and now the new corner points are 1, 2, 3, 4 and 5, right. So, the new optimal solutions. Now, what is the optimal solution? Interestingly, this new line which is 2x1 plus x2 less than equal to 6 is parallel to the objective function, right. Since it is parallel to objective function, it is very clear that this new optimal solution will be both these 2 by 2 2 and 3 0, right. So, the new integer optimal solution will be found. So, when you cut out, then now the new optimal solution are 2, x1 star equal to 3, x2 star equal to 0 and z star equal to 6. So, this is one optimal, and the other optimal is x1 star equal to 2, x2 star equal to 2 and z star is also 6. So, these are our two new optimal solutions, right. So, and both are integer. So, since an integer solution is found, we have found out the optimal value. So, this is the method, really speaking, that we solve the LP, we find the optimal solution, then progressively cut the solution space in such a manner, so that all the integer solutions are intact, but current non-integer optimal solution is cut off, right. And when the LP returns integer solutions, obviously that is the optimal solution for the integer linear programming problem. So, this is how the cutting plane method is used, but then I only showed the graphical part of it, right. How should it look in a simplex? So, that is our next task. So, let us, without wasting time, let us see how it is done. So, see, look here, now you want to solve it by the simplex methodology. So, again what we do, this is our original problem, then we make the augmented problem. So, the augmented problem is going to be like this, what we do, this is our original problem, then we make the augmented problem by taking two more variables, those are slack variables x3 and x4. So, we have 2x1 plus 5x2 plus x3 equal to, right, 17, 3x1 plus 2x2 plus x4 equal to 10, x1, x2, x3, x4 greater than equal to 0, and this is our augmented problem, which we write in simplex table 1. So, this is our basis x3 and x4, the current values are 17 and 10. This is our matrix, x1 and x2 are non-basic variable, x3, x4 are basic variable, they form the unity matrix, that is how simplex is done, and the matrix is written 2 5 3 2, and these are the profit coefficients, and these are also profit coefficients. To make 1 unit of x1, you need 2 units of x3 and 3 units of x4 at a cost of 2 into 0 plus 3 into 0, that is 0, and 2 minus that 0, Cj minus Zj. So, that part is Zj is 2 minus 0 equal to 2, and here it is 1. So, this is how we put the first simplex table. Now, usual method is followed to solve this problem, and then we see that the the 2 is more profitable. So, x1 is going to be our entering variable, and 17 by 2 is 8.5, 10 by 3 is 3.33. So, 3.33 is lower. So, x4 is the bottleneck resource. So, x4 will be our leaving variable. So, we found the entering variable x1 and leaving variable x4, right. So, these two are found, this is our common element. So, using them we can find the final solution, that is this simplex table 2. Now, x1 and x3 they are having canonical form 0 1 1 0, x2 they become now basis x3 and x1, x1 and x4, x2 and x4 they will be now non-basic and the values are computed. For example, 10 by 3, this 3 becomes 1, 2 becomes 2 by 3, 0, 1 by 3. Then this is the canonical form, this value which was 17 minus 10 into 2 by 3, so becomes 31 by 3. Is it all right? So, like this all these computations are done and we found an optimal solution, right. So, optimal solution is found and this is a non-integer. So, present optimal solution is non-integer. What is that solution? This solution is the x1 star equal to 10 by 3, x2 star equal to 0 and z star is 20 by 3. Please recall, in graphical solution first we found the LP optimal solution which is the same value. Alright, the same LP optimal solution we have found out. But now graphically we kept all the integer solutions intact and we cut off the solution space manually, I mean minimally, so as to keep all the integer solutions intact, but also to cut the present optimal solution. Now, how do we do that, right? How do we do that? That is our most important task now. How do we do that? So, look here now again, look at it very carefully. What is to be done that look at these two lines and look at the values. So, these values are there are two values, the 31 by 3 and 10 by 3. Now, what you do, the out of this value find out which one is having, listen very carefully, which one is having maximum positive fractional value. You see, what is 31 by 3? 31 by 3 equal to 10 and 1 by 3, which is 10 plus 1 by 3. So, this is the fractional part and 10 by 3 equal to 3 and 1 by 3 equal to 3 plus 1 by 3. So, this is the fractional value. The question is which one is having maximum positive fractional value? In this case both are equal. So, you could have taken either first one or second one, any one, anyhow we have taken second one. So, the second thing is equation, I mean second one is chosen. The second one can be written in this form. You see x1 plus 2 by 3 x2 plus 1 by 3 x4 equal to 10 by 3, is it not? So, that you can write this is our second constraint. Now, this second constraint can be written in this way, 10 by 3 can be written as 3 plus 1 by 3, is all right. So, the new constraint to add, this will be interesting, you take only the fractional part. See, x1 is not fractional because it has a coefficient of 1. So, it is the fractional coefficient part should be taken only. So, fractional coefficient is 2 by 3, here it is 1 by 3 and here the fractional value is 1 by 3. So, this is our new constraint to add, all right. For the time being, quickly let us see what would have happened if we would have chosen the first one. So, again let us see that, supposing we chose the first value because there was a tie, you see this can be written as 11 by 3 x2 plus x3 minus 2 by 3 x4 equal to 31 by 3. That is the equation, 11 by 3 x2 plus x3 plus minus 2 by 3 x4 equal to 3 and 31 by 3. So, these can be written as, so 11 by 3 it becomes 3 x2 plus 2 by 3 x2, x3 can be written as x3 and minus 2 by 3 x 4 has to be converted to the positive fractional part. So, what you can do? You can write 1 by 3 x 4 minus x 4 equal to, so 31 by 3, so 10 plus 1 by 3. Now, take only the positive fractional part in the coefficient and in value. So, this is the positive fractional part, this is not to be taken, this is the integer portion, this is also integer portion. So, this is also integer portion. So, this is the positive fractional part in the coefficient and this is the positive fractional value. So, taking this 3 into account, again you would have got 2 by 3 x 2 plus 1 by 3 x 4 greater than equal to 1 by 3. So, we would have got the same constant if we would have chosen the first constant line also. But look here, this point is coming because in both these constraints the fractional value part is equal, positive fractional value is equal, that is why it is the tie. Point to remember that whenever we have tie like this in the positive fractional value, it does not mean both consideration of both will give the same constant line to add, it may not be, it will depend on case to case. It is incidental that we have got the same constant line from both the constraints. In another problem another thing may happen, is it all right? And depending on that procedure may be little more lengthy, less lengthy, but whatever it may be the solution should be possible to find. Fine. So, we know the constant to add. So, if we know, then let us move over to our next slide and then we see how do I add the new constant. You see what we do is very interesting. We write it the negative way, right. We write in this manner minus 2 by 3 x 3 minus 1 by 3 x 4 equal to 1 by 3. So, this less than equal to will be then greater than equal to, and then here we add a variable say x 5 which is our slack variable. So, same thing is done here. So, minus 2 by 3 x 2, you see minus 2 by 3 x 2 minus 1 by 3 x 4 plus x 5 equal to minus 1 by 3. So, obviously, this should be minus also because 1 by 3 then will be, because we written in a negative way. So, that should be minus also, is okay. So, that is how we have put that constant here, alright. Now, moment we do that, we have to employ what is known as the dual simplex method. We do not have scope to explain what is dual simplex method exactly, but just remember I am telling you the procedure. The procedure is that we write the Cj minus Zj values and then these Cj minus Zj values we divide by the corresponding part. Suppose this is the minus, look at this, the leaving variable will be from the values which is most negative. Here only one value is negative. So, this x 5 will be leaving variable. Now, the corresponding coefficient for x 2 is minus 2 by 3. So, if I divide the Cj minus Zj by Aij, that means corresponding value in the row, then we get the absolute value of Cj minus Zj by Aij, and this is half here and this is 1 here, 2 here. We take the minimum, the half is the minimum, that is the procedure. So, the minimum, therefore, x 2 should be leaving, right. So, understood what we did? We have got the new constant to add, the new constant is put in a negative way, then put in the here and then use dual simplex because we have a negative value, then choose that particular constant as leaving variable which is having the negative value, in this case only 1. So, this will be the leaving variable and the entering variable will be the minimum value of Cj minus Zj by Aij. So, this is how we do. So, once we do that, then we find in the next slide that this is going to be our new solution space. So, what is the optimal solution we have found at this point? We found x1 equal to 3, x1 equal to 3. So, this was the table. By solving we have found this one by usual simplex, but then we have found x1 equal to 3 and x2 equal to half. Recall that this was our next point, right. So, this is the next value that we have found. Now, using that again we have to see that the values which is the minimum possible maximum possible fractional value. Again we have a tie. So, anyway we have taken the third constant. So, it is half. So, these half will remain and this is minus 3 by 2 can be written as half x 5 minus 2 x 5. So, this is the positive fractional part, right. So, this half, this is the positive fractional part and this is the positive fractional value. So, new constant to add will be half x 4 plus half x 5 greater than equal to half. Now, it is again added in the negative way. So, x 6 minus half. So, we added, you see the size of the problem has gone up, minus half, minus half, minus half and x 6 1. So, that will have the canonical form. Again we compute Cj minus Zj by Aij, right, and we have the modified simplex 3 table. So, then once we have this, then this is our modified simplex 3 table. When you solve by dual simplex, the good thing is at this point we find the integer solutions, right. We find the integer solutions and there is a tie in the entering variable, right. Depending on which one you choose following the dual simplex, we find these are the two solutions, right. This is one and this is one, and look here in this solution and this solution we have got the two integer optimal solutions. So, the good thing about dual simplex that once the solution is found at that level there is no need to really compute the whole table. Why? Because in dual simplex the problems are always optimal. You are moving from optimal, you are keeping the moment you have found something feasible, the problem is always optimal, but you are looking for feasibility. So, moment you have found a feasible solution, then you stop. So, we found a feasible solution which is integer, so we stop. Is all right. So, I have also shown both graphically as well as through simplex how do you use cutting plane method to find integer linear programming problem solution, right. So, thank you very much.